In this section, we're going to derive and then use some formulae for describing motion when we have a constant acceleration. These are often known as the Suvat equations, and they are given to us in the formula book, although we do also need to be able to derive them in this way if needed. So we're going to start with a velocity time graph, and we're going to consider an object that starts with an initial velocity of u. U is the letter that is used to describe initial velocity in this case. It's then going to accelerate at a constant rate until it reaches a velocity of v. So v is the final velocity, and the amount of time that it takes is time t. Now we know that the acceleration of an object is the change in velocity over time, and that this can be found by finding the gradient of a velocity time graph. So the gradient will be the change in velocity, which to go from u to v, the change in velocity will be v minus u, over the change in time, which from 0 to t will be t. So we arrive at this formula, a equals v minus u over t. We can then rearrange this to make v the subject of the formula, and this gives us our first equation of motion, or our first Suvat equation. This equals v equals u plus at. Next, we can use the fact that we know displacement is the area under a graph. Now the letter S is generally used for displacement. The area under this graph is a trapezium. We know the formula for a trapezium is a half of a plus b multiplied by h, where a and b are the parallel sides and h is the distance between. So adjusting for the letters that we are using, we get S, which is the displacement, the area under the velocity time graph, equals a half u plus v, which are the two parallel sides, multiplied by t, which is the distance between. This gives us our second equation of motion. Now the other three equations of motions can all come from these two, and essentially they all involve rearranging this first one here and substituting it into this second one here. For example, if we rearrange v equals u plus at to give us t equals v minus u over a, we can then substitute this into the second formula that we have. And simplifying this down, multiplying by 2a, we end up with 2as equals u plus v multiplied by v minus u. You will notice that this is the difference of two squares, so it would become v squared minus u squared. And therefore rearranging again gives us v squared equals u squared plus 2as. So this is the third equation of motion. We can now rearrange v equals u plus at, substituting it into this formula here. This gives us s equals a half u plus at multiplied by t. Expanding this all out gives us s equals a half 2u plus at multiplied by t. And then expanding this bracket leads us to this equation, s equals ut plus a half at squared. These equations of motion are sometimes referred to as the Suvat equations. That's because the five values that we use are s, u, v, a and t. They only work if the acceleration is constant. There is also a fifth equation, which is very similar to the fourth one. This comes from taking v equals u plus at, rearranging to get u equals, substituting it in, and you will arrive at this formula here, s equals vt minus a half at squared. You'll notice that there are five equations, and each one misses out one of the variables. So for example, v equals u plus at has four of the variables but does not have s. This second one here you can see has four variables but does not have a. So in each case you would look to see which variables you had and then select the correct formula from the formula book. Now we're going to apply this to a problem. So we've got a motorbike travelling in a straight horizontal line along a road. It's decelerating uniformly. Now uniformly is another word for constant. So if you see uniform here, you can assume that there is a constant acceleration. Decelerates tells us that the bike is slowing down. That means that the acceleration will be negative. We are told the initial velocity and the final velocity and the distance it travels. And then we are told it accelerates again and travels a further 1,560 metres in 75 seconds. We're going to answer these 4 questions using the Suvat equations. It's always a good idea to write down the values that you know or that you're trying to find out for S, U, V, A and T, and then you can choose which formula to use. So we know that S is 750, that is because this is the distance that the bike travels in the first part. We're actually trying to find the time it takes for the bike to travel in this first distance. We know that U is 26, that is because the initial velocity was 26 meters per second. We know that V is 14, that's because the final velocity for this section is 14 meters per second. And we are trying to find T. So we are looking for the equation that uses S, U, V and T. Looking at these, we can select this one. We can then substitute the values in and rearrange to find T. So if we rearrange this, we get a value of T of 37.5. Don't forget to use the units, which is seconds. So it takes 37.5 seconds for the bike to travel this first 750 metres. Part B, we now need to calculate the deceleration of the bike. Remember that deceleration is just acceleration, but it will be a negative value. So we're trying to find A. We have S, U and V. So the formula that connects those 4 variables is V squared equals U squared plus 2AS. So substituting these values in gives us this. We're trying to find A, so we leave it as A. We can then rearrange the formula, and this leads us to A equals negative 0.32. Notice that we've got a negative value here, which makes sense because we were expecting a deceleration. Also notice that we've put the units in for acceleration, which is meters per second squared. Always put the units in, even if a question doesn't ask for it. Now for part C, we're trying to find the acceleration of the bike as it travels a further 1,560 metres. Now be careful, in this second part of the journey, some of the variables have changed. The distance travelled in the second part of the journey is S equals 1,560, and the initial velocity is now 14. That is because the final velocity at the end of the first section is the initial velocity at the beginning of the second section. We know that this second section takes 75 seconds. We are trying to find A, so we need an equation that links S, U, T and A. So we can select this one here, substituting in the values that we've got and rearranging to get A leads us to an acceleration of 0.181 meters per second squared. Again, it makes sense that we've got a positive acceleration, as we do know that it is accelerating this time, it's speeding up. Finally, we want to find the speed of the bike when it's completed the further 1,560 metres. So we're now trying to find V. This is the final velocity for this section. We can use the values that we used in part C for this. The equation that links S, U, T and V is this one here. We can substitute the values in that we've got. Rearranging gives us a final velocity of 27.6 meters per second. Now pause the slide and have a go at these 3 questions, and then when you think you've got the answers, unpause to see if you've got them right. So in question 1, we are told the initial velocity of the van is 24. We are then told that it decelerates with an acceleration of 8 meters per second squared, so A must be -8. We want to know the time, and the 4th variable is that the car is going to stop, and if the car stops, that means that the final velocity will be 0. So for that we can use V equals U plus AT. Substituting in the values gives us a time taken to stop of 3 seconds. In the second question, we have an ice skater travelling with an initial constant velocity of 2.8 meters per second. Now she starts to decelerate when she is 4 meters past her friend and finally stops when she is 16 meters past her friend. So in this time, she actually travels 12 meters, so S will be 12. She's going to come to rest, so her final velocity will be 0, and we want to know the amount of time it took her to stop. So we're going to look for the formula that involves U, S, V and T. That's this formula here, and substituting in the values and rearranging gives us a time of 8.57 seconds to 3 significant figures. Finally, for part 3, we have a jet travelling with an initial velocity of 63 meters per second, and it then accelerates with an acceleration of 15 meters per second squared. We want to know how far the plane travelled, so we want to know S, and the time is 10 seconds. So we're going to look for a formula that uses U, A, S and T. That's this formula here. Substituting our values in gives us a distance of 1,380 meters. We're now going to consider what happens if an object is falling. So a ball is being dropped from a height of 12 meters, and we want to consider what will happen after the person lets go. So as you can see, the ball started at rest and it accelerated vertically towards the ground. This acceleration is due to gravity. So when an object is falling through the air, its acceleration due to gravity is denoted by the letter G. Gravity on Earth is taken to be 9.8 meters per second squared for this course. So we're going to consider if a ball is dropped from a height of 12 meters, what its speed will be when it hits the ground. Now, because we know it has a constant acceleration due to gravity of 9.8 meters per second squared, we can use the Suvat equations for this, considering the vertical direction of the object. First of all, we need to decide which direction is positive. It's often normal to consider the direction that the ball moves in as being the positive direction, although you will arrive at the same answer if you choose upwards to be positive, as long as you are consistent with all of your working. So we're going to take downwards as the positive direction. This means that S will be 12 because it's travelling 12 meters in that direction. U will be 0. This is because the ball is initially not moving. A will be 9.8 meters per second squared. This is because it's accelerating due to gravity. And we want to know the velocity when it hits the ground. We want to know V, so we're looking for the formula that uses S, U, A and V. So we're going to use this formula here, substituting in the values that we have got to find v leads us to a velocity of 15.3 meters per second when the ball hits the ground. We're now going to consider a ball being thrown straight up in the air. Its initial speed straight up is 14 meters per second. We're going to take the acceleration due to gravity as 9.8, and the point where the ball leaves the person's hand will be a height of 0. As we can see, the ball starts to travel upwards, it slows down until it reaches a velocity of 0, and at that point it comes back down again to the ground. We want to know what maximum height that ball reaches before it changes direction and comes back down. So in other words, we are looking for the displacement between where the ball leaves the person's hand and where it reaches the top. First, we're going to decide which direction we want to be positive. In this situation, it makes sense to make the upwards direction positive, as that is the direction that the ball is initially travelling in. Acceleration due to gravity is pulling the ball down. This is in the opposite direction to what we have called positive. So in this case, we are going to need to take a negative acceleration. The initial velocity will be 14. The final velocity, when the ball reaches its maximum height, will be 0. This is because it is at the point where it is changing from travelling upwards to travelling downwards. So momentarily, it has a 0 velocity. The acceleration will be negative 9.8. And we want to know the displacement for when it reaches the top. So we are looking for s, the distance it travels. We can use v squared equals u squared plus 2as. Substituting this in and rearranging gives us s equals 10 meters. So the ball will travel a maximum height of 10 meters before returning down to the ground. We now want to know how long the ball is above 6 meters for. We know that it reaches 6 meters because we already calculated its maximum height was 10 meters. So we want to know for how long it is more than 6 meters above its starting point. So for this, we need to consider at what point does the ball reach 6 meters? It will reach 6 meters once on its way up and once on its way down. At those two moments, the displacement will be 6. If we can find those 2 times, then the distance between those 2 times will be the amount of time it was above 6 meters for. Again, taking up as the positive direction, we can let s equal 6. The initial velocity was 14, and the acceleration is negative 9.8 because we have taken upwards as positive and the acceleration is downwards. We want to know the time when the ball is at this height. So we're using this formula here. So substituting this in gives us a quadratic equation. We can solve this quadratic to give us 2 values of t. The smallest one will be the value of t when the ball is on its way up, and the largest one will be the value of t when the ball is on its way down. Subtracting these two, 2.33 minus 0.525, tells us that the ball is above 6 meters for 1.81 seconds. Now have a go at these 3 exercises using the Suvat equations from the formula book. So far we've considered situations where the acceleration is constant, and for that we've been able to use the Suvat equations. We now want to consider what would happen if acceleration was not constant. In other words, the acceleration varies over time. A velocity time graph would be non-linear if the acceleration was non-constant. Constant acceleration gives us a straight line velocity time graph, so non-constant acceleration will give us a curve. In this curve, the velocity is given by v equals t squared plus 2 for t is greater than or equal to 0. This means if we want to know the velocity at a certain time, we can substitute that value of t into this equation. If we want to know the acceleration at a particular time, we need to find an expression for acceleration. We know acceleration is the change in velocity over time. So we could find the gradient of the tangent at that point. We know that to find the gradient on a curve, we can differentiate. So in order to find the acceleration, we can calculate dv by dt and then work out what this would be at time t equals 3. This would give us the acceleration. Differentiating t squared plus 2 with respect to t gives us a equals 2t, again for t is greater than or equal to 0. If we then substitute in t equals 3, we get 2 times 3, which is 6. So the acceleration at that moment is 6 meters per second squared. Suppose now we want to find an equation for displacement, and we've been told that the displacement is 7 meters after 3 seconds. We know that displacement is the area under a graph, and for curves this can be calculated using integration. If we integrate v with respect to t, we will get s, the displacement. So if we integrate v here, we get a third t cubed plus 2t plus a constant. We don't know this constant at the moment, but we can then use the extra information we were given to find that constant. If we substitute in t equals 3 and s equals 7, this will tell us the value of c. Substituting this in gives us c is negative 8. So therefore we have an expression for displacement at any time, which is a third t cubed plus 2t minus 8. We can then find the displacement at any time we want by substituting the t value in. So if we have got acceleration, velocity and displacement all in terms of time, we can use integration and differentiation to move between the two. Remembering that when you integrate, there will also be a constant of integration, which you would then have to find using extra information. So differentiating s gives us v, differentiating v gives us a, integrating a gives us v, and integrating v gives s. Now pause the slide and using integration and differentiation, fill in this table of values. When you have integrated some of these, you will need to find the constant of integration using this extra information at the bottom. When you've filled in the table, continue to check your answers. So, in the first instance, we can differentiate s to give us v and differentiate v to give us a. Notice that in this case we actually have a constant acceleration. In the second question, we need to be careful with the powers here. We will need to, for example, write the cube root of t as t to the power a third, and 1 over t cubed will need to be written as t to the minus 3. Differentiating displacement gives us this velocity, and differentiating the velocity gives us the acceleration. In the third situation, we can differentiate the velocity to give us acceleration, and we can integrate the velocity to give us the displacement. there is a constant here which we will need to find using extra information given at the bottom. For question 4, we can integrate the acceleration to give velocity, noting that we've got a constant of integration, and then integrate the velocity to get the displacement. And here we can see we get a second constant of integration, so we've called that k. We're now going to use this extra information to find the values. So for question 3, we're told the initial position is s equals 15. This means that if we substitute t equals 0 for initial, so t equals 0 and s equals 15 into this will tell us c. This comes out as c is 15. For question 4, we are first of all told that when t is 2, the velocity is 13. So in here, we can substitute t equals 2, v equals 13 to give us a value of c. That gives us 19. We can now use c equals 19 in here, and we can use the information that the displacement is 5 when t is 4. So we can substitute in s equals 5, t equals 4, and c is 19. This will give us a value of k of negative 47. We're now going to consider a situation where an aeroplane is preparing for takeoff, and over 4 seconds, this is the velocity of the plane. We want to know, during this time period from 0 to 4, what is the maximum and minimum speed? Now we know that maximums and minimums often occur at stationary points, so a good place to start is to try to find the stationary points of this curve. To do this, we're going to differentiate v and then set it equal to 0. dv by dt is 3t squared minus 10t plus 6. So setting this equal to 0 gives us 2 t values. Both of these t values are in the interval of time that we are considering, so both of these could be a maximum or a minimum speed. We could determine whether it was a maximum or a minimum by taking the second derivative to help us decide. At these two times, we can see the velocity. At this time we have a velocity of 3.11, and at this time we have a velocity of 0.369. So these potentially could be the maximum and minimum speed. However, to be sure, we need to consider what the graph would look like. Are there any points on the interval 0 to 4 where the velocity is either higher or lower than these values? Well, this is the graph from 0 to 4. Here we can see the two stationary points that we found, here and here. However, we can see that the end points also need to be considered, because in particular this point up here is much higher than this stationary point that we found. However, because it's an end point, it doesn't have a gradient of 0, but it could potentially be the maximum in that section. These maximums and minimums are local maximums and minimums, meaning that although in that small area that they are in, this is a maximum, for example, it doesn't mean it's the maximum on the entire graph. So we do need to consider other parts of the graph. To consider the velocity at the endpoints, we substitute in the time at 0 and the time at 4. At 0, we get a velocity of 1, and at 4, we get a velocity of 9. We can compare these two values to the maximums and minimums. We can see that 0.369 would still be a minimum, as it is still lower than this value here. However, we can see that actually the maximum velocity would be 9, because that is much higher than the velocity here at the stationary point that we found. So the minimum speed on that interval is the local minimum of the graph. V was 0.369 at a time of t is 2.55. And the maximum speed was the end point when t was 4, we got a velocity of 9. So to summarise, if you're asked to find a maximum and a minimum in a certain interval, start by differentiating to find the maximum and minimum points, but then also consider the values at the end points by substituting in the endpoint values of t into the equation for v, as these may give you a higher or lower value than the maximum and minimum points. Now complete these 3 exercises using the examples from the previous slides.